Diatomic molecules are probably the simplest of the molecules that one could encounter, and most molecules are somewhat more complicated, and this is certainly true when it comes to vibrations. In this case, particularly, a diatomic molecule has one vibration. So a harmonic oscillator is a perfectly suitable substitute for the entire vibrational picture there. We've already found that the partition function related to that single harmonic oscillator could be written something like this, where we got a vibrational temperature divided by 2T over 1 minus e to the minus vibrational temperature over T. So it's a fairly simple picture. What happens when we have a polyatomic? Well, a polyatomic, remember, is going to have 3n minus 6 vibrational degrees of freedom. Or if it happens to be linear, it'll have 3n minus 5, but I'll leave it at 3n minus 6 because that's the more general case. What kinds of vibrations are those? Well, the best I can do is describe for you using a simple model, a simple molecule, to show you what it might look like. If I have water, which is a bent triatomic molecule, it's going to have 3n minus 6 vibrational degrees of freedom. Well, the n is the number of atoms it has, so that's 3, so it's 9 minus 6, or 3 vibrations that it will have. In this case, the water's 3 vibrations, it could just be an individual bond vibration or something else, but in fact what happens is that water tends to organize its vibrations a little bit differently. It has one vibration where the two end atoms move out in concert with one another. This is a symmetric stretch vibration. It has another vibration where one moves in while the other moves out. This is called an asymmetric stretch vibration. And it has a vibration where the two bonds wag relative to one another. So this is either a bend mode or a wagging mode. Okay, but these are what the three vibrations look like. Now, what I've drawn for you here is actually something called normal modes. You don't need to worry about that designation so much. The real point, though, is that this polyatomic has more than one vibrational degree of freedom. And in many cases, at low energies anyway, we can write the vibrational energy for a molecule as simply a sum over the various vibrational modes. So, for example, I might have, in this case, 3 vibrational modes. So these three energies would correspond to the energies of these 3 modes. And I could write each of these as harmonic oscillators so that I would have h bar omega 1 times nu v1 plus 1/2 plus h bar omega 2 times v2 plus 1/2 plus h bar omega 3 times v3 plus 1/2. So this is actually very similar to a case that we've seen before a couple of times. When we took 2 molecules to make a system and we wanted to find the system partition function for those 2 molecules, it was just equal to the product of the 2 partition functions. When we wanted to take the various kinds of motion in a molecule and add them together to make up the total energy of a molecule, the total partition function for the molecule was just the product of all the partition functions for the various pieces. Well, the same is going to be true here, where we can just take, with multiple vibrations, we can take each of these as basically giving rise to a new kind of partition function, and it's going to be the product of those partition functions that gives us the final partition function. I'm cutting a few corners here, I realize, but what I want to persuade you is that the total vibrational partition function is essentially going to be the vibrational partition function for the first oscillator times the vibrational partition function for the second oscillator times the vibrational partition function for the third oscillator. And in this case, when I use harmonic oscillators, they're all going to have this functional form up here. So it means that I could, in effect, write, and I'll use a little bit different color just to emphasize this, I could write e to the minus theta vibe of mode 1 over 2t over e to the minus, 1 minus e to the minus theta vibe of mode 1 over t multiplying for a second oscillator, it would be e to the minus theta vibe of mode 2 over 2t over 1 minus e to the minus theta vibe of mode 2 over t times a third term, which would be e to the minus theta vibe of mode 3 over 2t over 1 minus e to the minus theta vibe of mode 3 over t. All right, so all we've done is effectively to make three partition functions out of harmonic oscillators and simply multiply them together. Now, one of the things I'll point out is that the numerators here all come from the lowest vibrational energy state, and none of them basically is energy that can be used elsewhere. So I could combine all of those together and say that they basically represent something I'll call V0 over KT. All right, so this might be a prefactor that we would put on our set of harmonic oscillator partition functions, and using this I could then write a general vibrational partition function that would look like this. It would be e to the minus the lowest energy state times a product for all of the various oscillators, all of the various modes in the molecule, so to say 3n minus 6 of these, of 1 minus 1 over e to the minus vibrational temperature for that particular mode over temperature. And so this is sort of a shorthand way that we could write a partition function for a more complicated polyatomic molecule. There's no shortcuts here, unfortunately, and so in this case we just have to deal with each of the modes. Now, one of the things that I want to really emphasize here is that each of these vibrational modes has its own unique frequency. So when I talk up here about water, these three modes, the symmetric stretch, the asymmetric stretch, and the bend or the wagging, are all different frequencies. So they will all have their own individual vibrational temperatures, again defined by this h bar omega over the Boltzmann constant. Now, this, I think, tells you pretty much what you need to know about polyatomic vibrations. We'll talk in more detail as time goes on about how they generally behave within a molecule. However, it's subject to the same constraints that we mentioned last time. A high frequency is going to lead to a high vibrational temperature, which means it's not going to have many states available. It's not going to be its higher energy states are not going to be very highly populated at a reasonable temperature.